Dear students, in this lecture we will discuss about vibrations of a stressed string. That is, we will discuss about one-dimensional wave equation d by 2 y upon d by t2 is equal to c square d by 2 y upon d by x2, which is a very important topic in boundary value problems in partial differential equation. Now let us consider a uniform elastic string of length L which is stressed tightly between 2 points O and A. Suppose this is x-axis, suppose this is x-axis, this is y-axis. Suppose this is the point O and suppose this is the point A. Now let us consider a uniform elastic string of length L which is stressed tightly between 2 points O and A. Suppose this string is stressed tightly between 2 points O and A, and a displaced slightly. Displaced means it be displaced like this slightly. Then what are the vibrations? We will discuss about the vibrations of that string. This string OA is the string which is tightly stressed between 2 points O and A and displaced slightly. When displaced it, then slightly from its equilibrium position. This is the initially it is in equilibrium position, there is no motion here, and when it is slightly stressed, displaced from its equilibrium position OA, then taking the end O, this end O is the origin and OA is the x-axis. This is the origin and OA is the x-axis, and a perpendicular line through O as the y-axis. This is the y-axis. We shall find the displacement of this y function of the distance x and time t. What we'll do here, we shall find the displacement of y function of the distance x and time t. Okay, if we slightly displaced from its equilibrium position, then what we have, it will be like this. Okay, and same here we have in negative y direction. Okay, now when we here we shall obtain the equation of motion for the string under the following assumptions. Here, when we are going to solve a problem of stressed string, then we will take some assumptions. What is number one? The motion takes place entirely in the xy plane. The motion takes place entirely in the xy plane, and each particle of the string, this is the string, and each particle of the string moves perpendicular to the equilibrium position OA of the string. Perpendicular means this is perpendicular, or move perpendicular, up and down, okay. It means the motion takes place entirely in the xy plane, and each particle of the string moves perpendicular to the equilibrium position OA of the string, okay. And the second point which we assumed here, the string is perfectly flexible. This string is perfectly flexible and does not offer a resistance of bending, okay. There is no resistance to bending. And third point is the tension in the string, the tension, okay, in upward direction and downward direction, the tension in the string is so large that the forces due to weight of the string can be neglected. And fourth important point is, which we are going to assume here, the displacement y. Here when we slightly move this string, then the displacement y and the slope d bar y upon d bar x are small, because the displacement are very small, so that their higher power can be neglected, okay. Suppose we have 2 points on this string. Number one, suppose this is the point P, and suppose this is the point Q. This is the point P and this is the point Q. And suppose on the x-axis this point is X, and here we have x plus del x, x plus del x, and distance between these two is del x, okay. Okay. Now, coordinate of this point P is xy, and coordinate of this point Q is x plus del x and y plus del y. What are the coordinate of this point P? Coordinate of this point P is xy, and coordinate of this point Q is x plus del x and y plus del y. X plus del x and y plus del y, okay. Let m be the mass per unit length of the string. What we assume here? Let m be the mass per unit length of the string. Now consider the motion of an element PQ of length del S. And suppose this is the length of this point PQ. Since the string does not offer resistance to bending, that is by assumptions which is we have assumed, the tensions T1 and T2 at P and Q respectively are tangential to the curve. Okay, here m be the mass per unit length of the string, and we consider the motion of an element PQ of length of this element is del S. Since here the string does not offer resistance to bending, the tension T1 and T2, here suppose the tension T1 means it's like a slope in downward direction. This is the tension T1, and suppose this makes here an angle, that is this angle is alpha, and this is the tension T1 in the downward direction, and T2 in the upward direction. This is the tension T2. Okay, and this angle is beta. Here the tension T1 and T2 at point P and Q respectively are tangential to the curve. Here these are the tangent on the curve. These are the slope T1 and T2. Okay, it is the downward direction and it is upward direction. Since there is no motion in the horizontal direction, we have no motion in the horizontal direction, means in this direction, because initially the string in equilibrium position OA, means there is no motion in the horizontal direction, because motion in only in vertical direction, not here in like this. So we have its component T1 cos alpha is equal to T2 sin alpha, T1 cos alpha equal to T2 sin beta equal to T. This we have assumed. Now, mass of element PQ. Now, what is the mass? Mass of element PQ. What is the mass of this element PQ? This portion. This is equal to m into del S. Okay, m into del S. M into del S. This is the mass. Now by the Newton's second law of motion. Newton's second law of motion, the equation of motion in the vertical direction will be, we have to write down this with the help of Newton's second law of motion. We have to write down the equation of motion in this vertical direction. What we know that from the Newton second law of motion, here we know that forces are unbalanced, means there is an acceleration. The acceleration depends directly upon the net force, upward direction and downward direction. Okay, that is tan beta and tan alpha, and the acceleration depends inversely upon the object of the mass. Here, what is the object of the mass? M into del S. This is the object of the mass. That is, by the Newton's second law of motion, the acceleration of an object is produced by the net force. Net force is this, tan alpha plus tan beta, but tan alpha in negative direction, in downward direction. That's why we take here minus tan alpha, and this is tan beta. This is beta. The acceleration of an object as produced by the net force is directly proportional to the magnitude of the net force in the same direction as the net force, and inversely proportional to the mass of the object. That is, the acceleration of an object as produced by the net force is directly proportional to the magnitude of the net force in the same direction as the net force, and inversely proportional to the mass of the object. That is what we can say, A equal to net force F net upon mass of that element PQ. Okay, the net force is equated to the product of the, or we can write here net force F net is equated to the product of the mass and acceleration. Okay. Now what is F? What is force? It is minus T1 sin alpha, because it is in downward direction. Net force, we add these two forces, T1 plus T2 sin beta, T2 sin beta. And what is the mass of this element PQ? What is the mass of this element PQ is m into del S, means here we write m del S. And acceleration, what will be the acceleration here? Here the mass acceleration of PQ acting vertically upward, means what will be the acceleration? Here acceleration will be d by 2 y upon d by t2. Here acceleration, how much an object accelerates depends on the mass of the object and how much force is applied to it. Means force equal to net force equal to mass into acceleration. Here acceleration of PQ, this PQ acting vertically upward is d by 2y upon d by t2. That is what we can write here. M del S d by 2y upon d by t2 is equal to T2 sin beta minus T1 sin alpha. Now dividing whole by T, that is m del S upon capital T d by 2y upon d by t2 is equal to T2 sin beta upon T2. Here T equal to T1 cos alpha and T1 T2 cos beta. Sorry, this is cos beta. Okay, but here horizontal, the component for horizontally T1 cos alpha and T2 cos beta. Okay, so T1, here we write this is the whole divided by T, T2 sin beta upon T minus T1 sin alpha upon T, that is m del S upon T d by 2y upon d by t2 is equal to T2 sin beta upon T. T means here we write cos beta, T2 cos beta, that is T2 cos beta minus from here this equation, and T1 sin alpha upon T means T1 cos alpha, that is m, or we can say m del S upon T d by 2y upon d by t2 is equal to tan beta, this is tan beta minus this is tan alpha, or simplifying this, what we get, d by 2y upon d by t2 is equal to T upon m del S, and this is what tan alpha and tan beta, what are these? This is a slope 10. What is 10 beta? This is a slope on point Q, that is day bar y upon day bar x at the point x plus del x. And what is 10 alpha? 10 alpha is a slope at the point here x, at this point xy, and this is a slope on this point Q, x plus del x and y plus del y. That is what we can write here. We can write here this del y upon del x at the point x plus del x minus del y upon del x at the point x. Here these two are representing slope. 10 alpha means dy upon dx, and here we have d slope means at this point P. This is the tangent T1 slope on this point, and on the point Q, this is the del y upon del x, that is slope on Q, and this is slope on P. Okay. Now what we will do, since here del s is equal to del x to a first approximation, and 10 alpha and 10 beta are the slopes of the curve of the string at x and x plus del x. Okay, this is the curve. That is, here approximately this point is x, this point is x plus del x, and we assume this is the arc length between P and Q, means approximately these two are, for a first approximation we can take these two and assume these two are equal. So we can replace here del s by del x. Now from this equation, day by 2y upon day by t2 is equal to t upon m, and what we have here, we have day by y upon day by x at the point x plus del x minus day by y upon day by x at the point x upon del x. Okay, that is day by 2y upon day by t2 is equal to t upon m. And what is this? This is the second order partial derivative with respect to x. Second order partial means we can write here d2y upon dx2 as del x tends to 0, or we can write it derivative to y upon derivative t2 is equal to c square derivative to y upon derivative x square, where c square equal to t upon m, which is a partial differential equation giving the transverse vibration of the string. It is also called one-dimensional wave equation. What is this? This is the partial differential equation giving the transverse vibration of the string. Transverse vibration of this string. And it is also called one-dimensional wave equation, which is called one-dimensional wave equation. Okay, I think this vibration of string, stressed string, how we can derive this wave equation, all you have understand easily. If you have any queries regarding this topic, vibration of stressed string, then you can comment on comment box. And if you feel some authors also used this one-dimensional wave equation as derivative to u upon derivative t2 is equal to c square derivative to u upon dx2, where c square equal to t upon rho. Okay, so we can take any of these two forms. Either we can have we in place of y-axis we can take either u-axis or simply we can take y-axis. Okay, now the boundary condition. Now what are the boundary condition? The boundary conditions which the equation this one-dimensional wave equation derivative to y upon derivative t2 is equal to c square derivative to y upon dx2 has to satisfy R. Actually, we have to, when we are going to solve the problem, there is no need to derive this wave equation. We have to focus on what are the boundary condition for this wave equations or given wave equation types of problems. Now, number one, y equal to 0 when x equal to 0, and number 2, y equal to 0 when x equal to L. Means these two conditions should be satisfied for every value of t. Here we can see here what is the length of what we assume. The length of this string is L. Okay. When y equal to 0, here we have y equal to 0 and x equal to 0, and here we have y equal to 0 and x equal to L. Okay, at the time t. Okay, this is the initial condition. Here we have y equal to 0 at here we have origin, y equal to 0 at x equal to 0, and this is the length of this string. The length of this string is L. Here we have on the x-axis y equal to 0 and x is equal to L. These two conditions should be satisfied for every value of t. If the string is made to vibrate by pulling it into a curve y equal to fx, and then releasing it the initial condition and releasing it, then releasing it the initial condition are y equal to fx when time t equal to 0 and divided by upon divided t equal to 0 when time t is equal to 0. Okay. Now, if the string is made to vibrate or it is displaced slightly from its equilibrium position, from OA, or string is made to vibrate by pulling, this is L, by pulling it into a curve. This is the curve y equal to fx, into a curve y equal to fx, and then releasing it, the initial conditions are y equal to fx at time t equal to 0 and y equal to then the slope and the y equal to and divided by upon divided t at the time t equal to 0. These are the boundary conditions which the equation of one-dimensional wave equation has to satisfy, and these four conditions are very important in every problem we will solve with the help of these conditions. I think this lecture is clear to all of you. If you have any queries regarding this one-dimensional wave equation, then you can comment on comment box, and if you feel this lecture is useful for you, then please like and subscribe this channel, and also you can press bell icon for getting further notifications about my videos. Okay, thank you very much. Have a nice day, and Bharat Mata ki Jai.